Good evening. Thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to focus on modeling and how it can help you in teaching AP Precalculus. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh. And with us tonight, I'm super excited to be joined by our two panelists, Gail Burrell and Rachel Gorsuch. Both these two ladies have been in the education industry for a very long time. Gail has a really large bio, but we have a lot of stuff that I want to get to tonight. And so I'll just leave it with that Gail is a senior math advisor with Texas Instruments and is out of East Lansing, Michigan. And Rachel, most notably, is currently teaching out of Columbus area and just recently finished publishing an AP Precalculus textbook, I believe. That came out last year, maybe. Am I kind of close? 2 years ago? Time's flying, I know. Anyway, so I'm really excited to have these two ladies with us here tonight to learn and grow. Speaking of learning and growing, Rachel, what's the plan for tonight?
Well, first, we want to welcome everyone. We love that the chat is keeping busy. Introduce yourselves. We're going to be asking lots of questions, so we hope you guys keep it busy. And then Gail's going to help us understand functions through modeling some real-world phenomena. We're going to be looking at wildfires in particular, and she has huge data sets I'm excited to look at. And we get to talk about rate of change, because if you teach AP Pre-Calc, you know that rate of change is a big deal. So Gail's going to take us through that. Then it's pumpkin season here in Ohio, so we're going to be looking at some of my pumpkin data that my students collected and comparing some mathematical models with database models. We're going to explore those functions using regression. And then I'm going to be talking about rate of change as well, concavity and end behavior. And then at the end of this webinar, we want to show you where you can find more activities on TI's website. And then we'll give it back to Mike to do a webinar drawing.
Thanks, Rachel. And Gail, what can we expect to be able to do by the end of the webinar?
Thanks, Mike. So we're hoping by the end of this webinar, everyone will be able to model data using functions. They will be able to describe characteristics of functions, distinguish between mathematical models and database models, and they know what kind of resources that they can get from the webinar and how they can get them.
So I'm super excited because whenever we were playing this webinar, there was something that was shared that I wanted to use with my students already. And so I think you're really going to enjoy a lot that's being shared tonight. The chat window, as Rachel says, is already active. So if you have any questions, feel free to get those asked. I know Rachel and Gail will try to get those questions answered. Again, we do have a lot to cover tonight, which is why it's really great that this is being recorded. And you will receive a link to the recording within a couple of days in your email so that you can watch this at your own pace and maybe go over anything that you feel like you need to see a second or third time. All right, Gail, it's all yours. Share your screen.
Thanks, Mike. Okay. There we go. So those of you that are teaching advanced pre-calculus know that the practices are an important part of what you should be helping students grow and understand how to use and why they're important. And so I just want to remind us about particularly symbolic fluency, because sometimes we ignore the need for kids to be able to move among the symbols very rapidly. The role of multiple representations, because sometimes I think we forget about tables and numbers, and then the obvious role of communication and reasoning. And so I'm going to start by showing you my wildfires. So these are
Gail, I'm going to interrupt real fast. I apologize, but can you put it in presenter mode? It's really small font when it's not in
sorry about
presenter
that.
mode.
I didn't even think about that slideshow.
No, you're all good. There's so much good data on here. I want to make sure everybody can see it.
Okay, so why can't I figure out where that goes? Okay, here it is, slideshow. Play from current slide. All right, better. Thank you, Rachel. Okay, so these are the number of acres burned in the wildfires in the year 2021. And there's a reason I'll tell you later why I'm using 2021 instead of the current data. But just look at that for a minute. And if there's something that you notice or wonder, you could put it in the chat. And so we could like think about what do you see that might be interesting? And so think about what you're seeing. And then I'm going to go, I think, to the question that I'm going to ask. Is there a relation between the number of acres burned and the region of the United States? So this is a question I care about right now. And so what I'm going to do is essentially, if you were in a workshop, I would go around and I would take that data set and I would give everybody a state and the data for that state, and then a colored sticky note. And depending upon the region of the United States that you were in, you would get a sticky note for that particular color. And so I've divided taken some common divisions. So I've got 6 different regions of the United States. And I've also made a number line at the front of the room, or sometimes if your room isn't big enough, you might have to do it on the floor in the hallway. But I've made a number line that goes from 0 to 2,100,000 or a little bit beyond. And that number line is what we're going to put our sticky notes for our state on that number line. So imagine yourself now, you're all sitting there and somebody has Texas and you've got the number of wild acres burned in wildfires from Texas. So now you're going to get up and you're going to go to the number line that I've got set up on them for you, and you're going to put your sticky note there. And this is what's going to happen. And so you're going to look at that and you're going to say, oh, now what's going on here? And the students are going to go and they're going to look at this. And if you think about what do you see, what's going to happen, if you think about what's going on and you're like, okay, what am I seeing here? And it turns out that everybody is piling up at the left end of my number line. And so I'm like, okay, you guys, go sit down. So my students all go back to their seats and I pose the question, okay, what are we going to do? And you can type in the chat, what do you think we might do? How might we deal with this? Rachel, if you could tell me what's going on in the chat, that would be great. So if people have things to say.
Yeah, I love it. And while they're typing in new stuff, Gail, I wanted you to hear about their notice and wonders. So previously, when they were just looking at all that data, Cherry said that she noticed that the Northeast area has significantly lower numbers of acres burned. And Val pointed out that when you look at California, there's a lot in California. And now Claire's saying we've got to rescale this graph somehow. Since so many are bunched up in one space, we have to rescale it. Or Rochelle says we could look at one region at a time if we wanted to try to break it up instead.
Cool ideas. And I want to follow up on that rescale. What could we do? How might we think about rescaling? Now, I will tell you that sometimes what my students want to do is just cut out the middle part that's not being used. And so then just like, okay, and I'm like, well, we can't really do that. I mean, you can't just not use part of your graph. You have to, that's not mathematically sound. And so even though that feels like a good way to do it. And then of course, if you're actually working with younger kids, they don't care if everything's in a scale. They just put all the numbers in order and ignore the scale. And so we have to figure out a way to rescale. Anybody having a thought about what we might do to rescale?
Yeah, so Gabriel is pointing out there's certain outliers in there that we have to account for, and Cherry's wondering if we should use a semi-log plot.
Oh, I don't even know what that is. How would I ever use a semi-log plot when I have not a clue what you're talking about? I got to stick with something here that I could really understand. Anybody have any other ideas? It's not so sophisticated.
We're gonna build our way up, right? We just did a number line with a bunch of smiley faces and stick people. I guess we need like a middle step between that and semi-log plots.
A bar graph? I'm interested in the bar graph, but I'm a little worried that I'm not sure I would get my order there. I might get quantities, but I would have a hard time with my stickies, and I really like to use the number line if I can.
Jill's trying still like building on that idea of removing outliers and maybe having a separate conversation about those.
Okay. So because we're online and we're in a time crunch, I'm going to actually um, ask Rachel, what am I going to do, Rachel?
I mean, I think we have to start thinking about this in just a little bit different way. And the first thing I noticed is everything on your number line is powers of 10. So I wonder if we could rewrite this as powers of 10 instead. That was starting
Ah,
to bring up the idea of logs too. This idea of powers of 10 and logs, maybe.
so remember, I don't know anything about logs because I'm a kid now in my Algebra 2 class or my Precalculus class. And I really didn't understand logs when I was in in Algebra 2 anyway. So now that I'm in Precalculus, I'm, okay, that's kind of fake. So, all right. So I'm going to actually rescale in powers of 10. So I'm going to take down all my number line and everything else. I'm going to start over and I'm going to get a new number line. And that new number line is going to be in powers of 10. So now when I send everybody up with their sticky notes, they all go up there and they post their little sticky notes. And now there's room. And so that's kind of cool. And so basically, what I end up with is a plot that looks like this. And now I can actually look at that plot and I can say, well, do I see any pattern? And somebody offered that the Northwest, and the Northwest is, Northeast. The Northeast is the green, and the green, you were right, the green doesn't, it's got lower number of acres burned than some of the other ones. And it looks to me like the red, and the red is coming from, where is that? The West Coast, and the orange is coming from the Northern Rockies. And so it looks like maybe there is a relationship there. And I'm like kind of excited because I can now answer my question. And the big deal here, the reveal, is what you guys were trying to get to right away. But rather than starting off by telling you that we were using logs, and so when Rachel first made our agenda, she wanted me to say, okay, we're going to explore logs. And I was like, no, this is the whole point of this is we want kids to see why logs are important. And the reason they're important is because it allows us to rescale when we have things like outliers. So we can go either something is really, really very big, like California was, or if something is really, really very small, and other kind of data that you have, and logs allow us to rescale that. And so we've made this scale in logarithms, but really logarithms are exponents, which my kids never understood. Um, as a matter of fact, one time some kid in my calculus class announced a logarithm is an exponent. And I was like, yes, I've been trying to tell you that for days, and it finally sunk in. Okay, so basically that's what we've done. We've had a plot that had a serious outlier, California. You can have a couple of outliers either direction, and we've rescaled them in logs. And so I've done it here, what it looks like if you did on the 84, if you did it on the Inspire. But there are some things to think about here. So one of the reasons, and I told you why I used the 2021, is because Delaware is 0. And where do you put Delaware? Because you can't get 0 out of 10 to a power. So where do I put Delaware? And this is like, the kids are like, okay, well, I don't know. And then this one time I did this and somebody said, oh yeah, but look, I figured that they had to have a brush fire or a bonfire in the backyard. So I figured it was really close to 0. And so I put it on 0 anyway. I just rounded. And then Rachel had this really good comment. Rachel, what did you say?
Well, I wanted to go with powers of 10, but I think a lot of my students think that when you start with powers, you start with 0. And I'm trying to get them away from that. So I thought that maybe I would put it at 10 to the -1 for the same reason. Maybe someone had a really big bonfire in their backyard. And so 10 to the -1 made more sense to me.
And that's really cool because what is 10 to the -1? It's
1 over
1/10.
10.
And 10 to the -2 is 1 over 100. And that's partly what I meant about how we don't pay enough attention to the numbers and the tables, because that's a big reveal here, is that that's never going to go down. It's going to go down here. The other big reveal is that kids think that because every scale should be linear, should be halfway between the numbers, but in an exponential scale, in logarithmic scale, that's not true. And so when you start asking the kids to talk about questions like, what do I do between, is 10 to 3.5 halfway between 10 to the third and 10 to the fourth, they actually come to, oh my gosh, maybe not. Maybe where I posted my sticky note is the wrong place. So you can actually let them go back up and fix their sticky notes if they've made some wrong assumptions about the size of their numbers. And then this was a big reveal for my calculus class, actually, because I told you they didn't always get this stuff. When I said, let's try different bases, they were like totally blown away that the different bases would be the distributions are identical. I mean, if I use the ln, the natural E base, if I use the base 10, if I use the base 2, the distributions look like they're totally, one could be pasted right on top of the other, they're congruent. The difference, though, which the kids actually have to pay attention to, is your scale. Sometimes we don't pay enough attention to scale and we don't really think about that. But obviously the scales go from 4 to 14, from 2 to 6, from 6 to almost 20. So it's the scale. It's then there's a transformation that's going on there, and that lets you have some other conversations about some other kinds of mathematics. So this is all kind of like really cool. And now, Mike, tell us what you did.
So this was pretty impromptu. Like we were just doing some planning, and I was like, I need to do this with my calc class because again, I had the same feeling that Gail had, that my calc students didn't really understand. Like they saw logarithms like in this vacuum, like it was this totally separate area of mathematics. I'm like, I need them to make this connection. So I did something similar where initially Gail was like, you need like 30 feet. I'm like, 30 feet? Like I don't have 30 feet. I'm like, wait, if I go outside in the hallway, I do. So I just used like that craft paper, I think is what it's called, and just measured out 30 feet and did my best to make a number line, taped up the lockers, and put the initial scale that Gail had showed where everyone kind of gets bunched up to the lower end. And I was hoping that my panoramic shot would kind of show it, and it kind of does, not that great. But you can see that first picture that all those sticky notes are all bunched up to the left. And so I did something similar where I called all my students back and I said, does this look like something that we could like answer a lot of questions about? And they started talking about really more of the stuff to the right. They're like, well, these points down here seem really unusual compared to everything else. I'm like, okay, I agree. That's a good observation. But what if like we wanted to talk about that huge bunch? Like, how do we start to spread that out? And I had a couple kids that are pretty on it, and so they suggested that we use exponents. And I didn't expect that they were going to get that fast. But the second picture is once we did spread it out with exponents, we could certainly start asking some of the questions and answering some of our initial questions we had. So it was a lot of fun. It was a good, I think, a good connection activity between exponents and logarithms. So thank you.
And if they get that now, that's going to stand them in good stead. And if they could do it in pre-calc, then you wouldn't have had to do this in calculus, which would be even better. So I just want to throw in a couple little things here because I thought this was interesting. So one of I think we don't make enough make it clear enough to our students that most of the developments in mathematics came because of trying to address some need to describe the world that we live in. So out of navigation and location, that's where we got an awful lot of our mathematics, and that's where this whole idea of logarithms came from. The fact that we needed some way to deal with the kind of physical world that we live with. And the other thing that I thought was really interesting, I didn't know this, that logarithms came before exponents. And there's a little MAA book that's in here, and you can get the slides. So this is like just a really interesting little tidbit. I just always thought that, first we had exponential functions and then logarithmic functions came, but I didn't. And the other thing that logs are really good for, if you are in statistics and you care about some of the regressions, log really straighten up, because of this rescaling business, logs straighten out your data. So if you're looking for some way to model and you can straighten out the data, and you can use a linear modeling, which is mostly what they do in the world of statistics. The other thing that there's a Gapminder. If you've never looked up Gapminder, just Google Gapminder World, and they use both logarithms and linear scales, and you can go flip back and forth for their data, and the kids can get a sense of how what the logarithmic scale really does and how it behaves, and that's another way for them to see these cool things. Okay, so I'm going to rush through a couple of other things here. So that Rachel has time to talk with you about the pumpkins data that she has. And so we want to, now when we're dealing with functions, we want to actually pay attention to some of we've got this logarithmic function now. We know what logs do, they're exponents. So if I would put this up on the graph, and I would say to the students, describe the function f. And here it's really visible. This 1/10 business is really visible, and 1/100th as it's depressing, as it moving in there. And so then I would want to describe the rate of change of f. So like Rachel said, rate of change is all over. And now I'm going to try to do something that I hope I can do if I remember right. I'm trying to go to my 84. Man. Okay, so there's my log function. And if I look at a graph, there's my log function that I
Actually,
graph.
Gail, I'm going to pause you for just a second. We don't see your 84 right now. We still see your presentation mode.
Why? Okay, Mike, why?
It might be because you're in presenter mode. That might be what it is.
Gail, if you move your mouse to the very bottom where you have your task bar and just hold it down there, because you're still in that screen sharing mode, it should let you bounce back.
Okay, hold my mouse down here.
Yeah,
Down at the bottom.
does your taskbar pop up if you go all the way to the bottom?
Okay. I don't know what it's doing.
And if not, then just can you press escape and maybe go out of that full screen PowerPoint mode?
Escape. I went out of escape. Okay.
Oh, you know why? Wait, I know why. Gail, you need to stop sharing. You're sharing your application and not your entire screen. That's why.
Oh,
Sorry.
stop sharing.
Yep. And then share one more time, but don't share just the application. Share your entire screen.
Oh, I know what I did. You're right. I get it now. Okay, so this time I want to, now I shared my application. Now I screwed it up again.
Well, that's okay, Gail. While you take time to
Okay,
do that,
I'm
I
doing there.
actually wanted to give a shout out to a lot of these applications that people are putting in the chat, using the Richter scale to talk about logs and decibel levels and pH and chemistry and computer science. So Gail, the chat just has so many good examples going on that we're glad you took just an extra second to pull up your calculator so we could talk about those.
Okay. So now you're all seeing my 84, right? Okay.
It's correct.
So I'm going to create this log function in my stat lists. So I'm going to actually go here. I'm going to go up into list 1, and I'm going to seed list 1 with a list from a sequence, and you can find it under ops 5, and I'm going to set up my XX increments of 0.05, start at 0.05, and I'm going to end at 10. And I'm going to go through and I'm going to paste that in. So there's my increments. This is going to be my input for my function that I'm going to look at. I'm going to go over here to the list 2, and I'm going to seed list 2 with my function value that I have in y1. And so I'm going to the y-vars, pick up my function. And I know there's ways you can get this faster, but I'm always slow. I do the painstaking one. And what do I want my input to be at? I want my input to be at, my output to be at using my input. So I want my second L1 here. And I'm going to click my enter. And now I have an X set and a Y set. And I want to figure out my rate of change. So what's rate of change? Rate of change is delta Y over delta X. So delta Y over delta X. So I'm going to go to back to my list 3. Now I'm going to fill list 3 with that rate of change. Now, where do I get that? I go to my list and I go over to my ops. And I bet you never knew that this little guy right here is delta list. So he's the way I can find my change as I go the incremental change from one point to the one row to the next row. So I'm going to 7. Well, I guess I got to go down this way. Okay. And I'm going to do my delta list of my, now remember what this is. The rate of change is the change in the Y over the change in the X. So I need second L2 because that was my Y value, right? And I'm going to divide that by my rate of change back to my ops to 7. And this one I want my second L1. And I'm going to close my parens and I'm going to hit enter. And now I have my rate of change. And so let's just look at that just for a little minute. So what do you see in these numbers? Remember what these numbers are. It's the difference between, I'm subtracting the rate of change, the change in the Y over the change in the X as I go down my list. So if I were to find this difference and divide it by that difference, that's how I should get that. Okay, and I'm going to try to do a graph here. Because I did difference consecutives, if I look up at the top, there's a missing value here, right? Because there was one that wasn't there. So I'm going to fill that in. And if I can just fill it in with 0.1, because it's close enough, it's like going to be that. So now I have the same number of things. Okay, so now here's my really big question. If I going to graph my rate of change, what am I going to get? So I'm going to go down here to plot 2. I'm going to turn it on. And I'm going to make a scatter plot of L1 and L3. So what do you think you're going to get? Type it in the chat. What do you think that graph is going to look like? Got people
So
thinking?
Gail, the first thing that we see pop up is it looks like the rate of change is decreasing, and that's our starting point. I'm sure people are thinking and getting ready to type in more. Vignay is saying maybe a logistic. Any other ideas?
Okay, well, I'll take you out of your misery because we have to get onto the pumpkin data. Rate of change is decreasing. That's like good. Okay, so we're going to look at the graph and I'm ready to graph. I guess I got it set up. There it is. So now remember, this blue guy was my function. That was my logarithmic function. This red guy, this black guy is my rate of change. And I'm not going to take the time to actually, no, let's see if I can do this. Okay. Command tab. Oh, I want to go back to my PowerPoint. Think it should let me do that now, right? Back at my PowerPoint. So this stuff is all here in case you want to see it. Okay. So here's my rate of change. And here's the questions that are really important for you to answer and ask of your students. Because as calculus teacher and as a grader for AP Calc, the people that I grade and my students never understood the difference between the rate of change of the function and the rate of change of the rate of change. So they got these ideas mixed up, and that's a really important thing for kids to know. And so this is why I'm looking at the rate of change here that I've graphed. And if I think about this, the difference between the function and its rate of change, you can have a nice conversation with your students. You can make a conjecture. I'll just share quickly the conjecture. And if you do a regression, it's the rate of change is 1 over x, which is, those of you that teach calculus would know that the derivative of the logarithm, which is the derivative, remember, is rate of change, the derivative is 1 over x. And that's all there in case you wanted to look at it. And I don't think I have enough time to really go into this, but if you want to do end behavior, holes, and asymptotes, Rachel is going to come back and talk about this. But the deal is, don't forget about the table and the ask function, because that is a really important way to understand how the end behavior and how things behave around asymptotes. This is another good example. I don't want to take time to go through it, but it's another great example of a logarithmic function that appears in the press. And now, Rachel.
So as Gail said, we probably had enough for 3 hours, but we're trying to keep it close to 1 hour. So thank you guys so much for adding stuff to the chat. And as Mike mentioned, we're going to share our PowerPoint with you. You'll have the recording, and we're actually going to send you out all these data files for the TI-84 and the Inspire, including this one. So every fall, my school is about 15 minutes. I'm from the Midwest. We tell time or distance in time. So we're 15 minutes away, even though I should say like 4 miles, but from the Circleville Pumpkin Show, which is the biggest pumpkin festival on the East Coast. To those of you in California, we can't quite hang out with Half Moon Bay. You do have a bigger festival than we do, but we try our best. And so what I've tried to do is have my students really just dive into the math behind pumpkins. Now, I teach high school, but we have found a way to bring in our kindergarten friends and our middle school friends, and we collaborate and we collect data together. And it's been really fun to see students at every grade level collecting data. So, just a little context. This is student collected data. So there might be some problems with it, but it's pretty good, and they get a little better each year that they do this activity. The pumpkin number is just a number I put on the bottom of the pumpkin as an identifier. So that's nothing mathematical, it's just a name. And does anyone have a guess what ribs might be? So if you're looking at a pumpkin, what do you think the ribs might be? Give you a second to type that in the chat. There we go. I love that there's so many ways to say it too. The indentations, the divots, the seams, the lines on the pumpkin. You're exactly right. I have never gotten a definitive answer on what those are called. I saw an elementary school teacher call them ribs, and I thought, you know what? She must know I'm doing this. So that's what we're all going to go on. And folks, my students measure in centimeters, and surface area was in centimeters squared. Weight we did in grams, and so on and so forth. Okay. So what I would love for you to do in the chat is tell me what two variables, in other words, headings, do you think might be related, and why do you think they're related, or how do you think they're related? So I'm going to give you a moment just to type some stuff in the chat. Honestly, the numbers are small because I don't know that they're as important as thinking about those relationships between the headings. And so I'm curious what you have to say. Which headings do you think are related, and how would they be related? Val, just for you. I did metric just for you. See, now we're just having a bunch of metric system love over here. What about those variables? So solid, they're all related. Tell me how. How would you relate these? Okay, Rebecca says diameter and circumference. What do you think the relationship between diameter and circumference would be? Okay, radius and circumference. We've got this pi is coming into the play here. Everything is going to be related to radius, Monique says. Surface area and volume seem to have the same shape. Okay. So the reason I'm pushing you all to think about these variables and how they're related is I actually want to start by thinking about mathematical models before we start thinking about data modeling. And this is something I want my students to do too. I want them to dig back into geometry, into their middle school math. How are things related mathematically, and what formulas do we know for that? So folks, put some happy formulas in there. How do you think, what's a formula you have that relates circumference and radius? Everyone's trying to figure out how to type this in without having math type. It's so much harder. Love it. So we've got pi times diameter in there. What about area? How could surface area be related to radius? Because these are the mathematical models we're thinking about right now. Ooh, some fancy that with the italics. I don't even know how to do that, Jeanette. I'm going to have to learn how to do that. A equals pi r squared. Okay, surface area is 4 times pi r squared. So what we're trying to do right now is really gravitate towards some mathematical models. And this would work pretty perfect if pumpkins were spherical or if pumpkins were cylindrical, but we know that they're a little bit messy. And that's one of the reasons I like doing this with students, because models are messy. Models are often good enough. They help us understand something, but they're not normally going to be perfect when we do a data model. Mathematical models, we can make precise. Whereas data models are often a little bit messy and we have to do the best we possibly can. Hannah, I like that clarifying assumption. I think that's a big part of modeling, is just saying, I am envisioning it this way, and this is leading to my thinking. This is why I think this is the best model. So when Hannah said, I'm thinking of the pumpkin as a sphere, and therefore I have this math model, I think that's really good. So Gail, we might not even need this next slide because they just kind of took it and ran with it. But will you go to my next slide? So I was trying to figure out what shape is a pumpkin, and you guys kind of started leaning into it, especially Hannah, that was intro. Much I appreciate you. So this idea that most students think of pumpkins as spheres, and maybe they're thinking of like those traditional round, we call them pie pumpkins. But what if you get those tiny little cute ones? Would you describe that as a sphere? It's true, Stephen. You know, we're trying to like describe something that's not perfect, but in a perfect world, you know, what would it be? So those little tiny ones, or even great big jack-o'-lantern ones that are way taller. I'm trying to like, I've got this tiny little screen. I gotta get my hands to fit it. So we have a tall pumpkin. It's kind of narrower. It's probably not so much a sphere, but it's not exactly a cylinder either. And so this is the problem my students have to, John, that's what I'm talking about. Some of them are way more cylindrical in shape, but this is the problem that my students are running into. And this is the problem I want them to think about. And they've even decided to do sorts sometimes. I'll tell you what, the best students at sorting pumpkins are my first graders. You ask them to just sort them and then have the other groups do the measurements. First graders are amazing at that. So anytime you can do this activity cross grade levels, you're going to get much, much cooler data because of the way that each student at each grade level is interacting with 3D objects. Oh my gosh, Val, I want to see it. I don't know what a spherical cylinder is, but like, I'm gonna like, yes, that's exactly what I need. Okay. So we've already talked about a couple algebraic models. For instance, circumference is 2 pi times the radius, or area is pi times radius squared. So these are mathematical models where we have this value, radius, and we're building a model off of it. So let's use that as the context for how we analyze our data next. So I'm going to, again, Mike is going to send this out to you as a file when you guys are done with this webinar and you've had time to like think about it and you're ready to try it on your own. You will get this data file. But I'm going to go ahead and share my screen now.
Oh,
And one of the things that I think benefited me a lot as a TI instructor and as a teacher was learning where I could find big data sets to give to my students and how I could put them onto the calculators that I had at my school. Now, I've taught at schools that are all Inspire, and we could send stuff out through the navigator. And now the school I'm at, we're like a TI-84 school. And so this was a game changer for me. What I realized is I could download one of these files that has all this data. And if I go on the SmartView software here to this little, I don't know, let's call it flying paper, I can actually hover over this little computer in the top corner and I can add content to my emulator from my computer. So I have this file. There's Gales Acres Burn. We're sending that to you as well. But I'm going to pick up my pumpkins. And it asks where you want it to do it. I normally just let it tell me where I want to go because it normally does a good job. But I like that it's going to store it in my RAM, so it's going to be accessible. And now in my list of lists and everything like this, we've got our pumpkins. And so I'm going to go ahead and head back to my calculator screen. I'm going to go down to the program because that's what this is. And it was written in TI Basic. Sometimes we write them in Python, sometimes we write them in Basic. And I'm going to execute pumpkins. And our good friend Dan Wilkie actually took so many values from my students and programmed them in for you guys so that you could have a nice large data set without having to do this yourself. Or maybe I should give credit to Gail. I think she added 3 columns on for me as well. It just kind of keeps morphing is what happens. So we have all this pumpkin data is now stored in our calculator. And when I go to stat, edit, I can actually see that it's replaced on my lists. L1, L2, L3. And so I could always go back in and add my list back in. But I just want to focus on this for right now because you already gave me some really nice mathematical models, and I want to see, based on their context, if the data representations work with this too. So you can see we measured the radius and the height of the pumpkin, the weight of the pumpkin, and what else do we have in here? We also have some of those natural logs. You know, Gail's been working on it. If there's some logarithms in there, surface area, circumference. So let's start with circumference. That was one of the first ones that was mentioned. Let's see if there's a relationship between the radius and the circumference. So we'll go to our stat plot. I'm going to turn this first one on. And when I go to my X list, normally I would use L1 and L2, but we're going to go into the list, second list, and instead of choosing those list names, I'm going to choose I'm kind of using radius as like an independent variable. And my Y variable, let's do circumference. And so now when we graph this, well, first of all, our data is a little bit bigger. So I'm going to use zoom stat to try to see this. Folks, tell me in the chat, is this what you expected to see when you were talking about that relationship between circumference equaling 2 pi radius?
Rachel says, yep. Yep,
It's
they're
mostly
happy.
linear.
Yep.
It's really nice when it works out that way. Now, once again, I have first graders through 12th graders working on this together, collecting a bunch of data. So it's never quite perfect, and that's okay too. I tell my students, data isn't supposed to necessarily be perfect. It's supposed to be what we observe. And so I even have my students go in and do a regression on it. So if I go to stat calculation, our context says it should be linear. Our visual says it should be linear. So we can do lin reg either with ax plus b or lin reg with a plus bx. I'm going to go with this one for right now. And once again, students aren't quite used to this idea of going in and having to find these names in the list. They're used to using L1 and L2, but the more you do it, the more they get used to it. And I'm going to store that regression equation real fast. Gail, I know that there's hotkeys, but I also just go in and I like to store it using the long way. And I don't know why. I really don't. But so we've got this nice equation, and if I want, I can graph that equation through there. And let's go back to that for just a moment. So I want to see that first function, y1, parentheses, x. I just want to see what that function was. Oops, I should just do y equals, that's faster. So, ladies and gentlemen, let's look at that slope. How does that slope relate to what your ideas already were about the relationship between circumference and radius? Isn't that so cool? I'm seeing 2 pi pop out, like we're on it. And this is where it's really amazing for my students because they didn't that pumpkins could teach them math. And they didn't think that there was this 2 pi idea was kind of abstract to them. I mean, it's literally Greek to them. And yet now they're like, wait a second, I've got this number, 2 pi, 2 times roughly 3.14, and it's really close to what my graph is showing me. And so it's this really nice way of getting students to think about context and mathematical modeling when they're analyzing data and making sense of it. I want to do one more, also keeping an eye on the time here. But because we do want to talk a little bit about end behavior and concavity, I push my students towards some of those other relationships. And so one of the things that was mentioned was, let's talk surface area, radius versus surface area, and see what that looks like. So I'm going to go to my list and surface area. I knew it was in there somewhere. There's a cool relationship with the weight too. If we do that one later, looking at the time, I don't know if I'll have time to do that, but watch the recording one more time. And when you get the data set, play around with the weight. It's a good one. So we've got radius and surface area on there now. Let's see what that graph, oops. See, this is where I made a little error because my stat plot still had, oh, no, I have radius and surface area. I got ahead of myself. But we'll go back to that graph and do a zoom stat just to see that data. I'm going to turn off that graph for just a moment. We'll put a new one in just a second. But folks, did this graph end up looking the way that you thought it was going to look between radius and surface area? Let me know in the chat. This one's not as nice scale. We have to think about it.
They're thinking. I will say that my friend Tom Dick, some of you may know Tom, this surprised him a lot. He's like, oh, what's going on here?
We always want to figure it out. And what I tell my students is a lot of them are like, no, this isn't right, because in surface area, there should be something going on with like radius squared, right? Like they're trying to process it. I'm like, yes, I love this. This is what I want you to be thinking about. And so they're trying to figure it out. And they do one of the best things, Gail. It makes me so happy. They made me a better teacher because they pushed for this. They said, Miss G, it is not enough for you to give us a graph. You need to give us pictures of the pumpkins because we want to understand it. And I was like, I love you guys so much because they're trying to make sense of it. And what happened was those big jack-o'-lantern pumpkins, those are those outliers that you guys are describing. And then all the rest of them were pie pumpkins. And so while they're all pumpkins, they were different kinds of pumpkins. And so it's kind of throwing off this idea of a radius and surface area because we were mixing in ones that were very cylindrical and tall with this standard, more spherical pumpkin. And so this is why all of you are asking exactly the right questions in the chat. This is why this data doesn't look like the mathematical model that we were expecting. Melissa, I did. And it wasn't to be tricky. I did get you, but it wasn't to be tricky. I should have put a picture up at the very beginning of this. But I love working with adults who are asking these questions that my students are asking. You just have more life experience to ask these types of questions, where my students, they really need that visual. And so I geek out so hard about all of this stuff. I do want to test. Let's see what a quadratic would look like in this. Let's see if it's a decent model. So we'll go over to calc and oops, sorry, I grabbed the wrong function there. We're going to do, instead of a linear regression, let's do a quadratic regression. Our X list, we're going to keep that with radius. Our Y list, we're going to switch over to surface area instead. It's also really funny when students do this as freshmen, they don't really measure very precisely. And then a couple years of doing this with other students, and they start to get very specific about their measuring because they're like, no, it'll give us better data. Trust me. I'm going to go ahead and store this regression too, just because I think oops, sorry about that. I got ahead of myself. Anytime I talk about my students, I get so excited and I kind of get ahead of myself. But I'm going to store it in that Y1 value just so we can see it next to each other. So we have this beautiful quadratic. When I graph it, I mean, that function isn't bad. It's not exactly great, but two things that we're supposed to keep an eye on in the curriculum for AP Stats are we should look at the context. Does it make sense? And it kind of makes sense, but we should also look at the residuals. So when you get the chance to look at residuals, do it because it kind of helps you understand how far each one of those data points is away from your model. And you can see where your model is kind of leaning away from data points or leaning towards it. So you can see where it's over and under predicting for your data points. The way that we can see that scatter plot is we can, I'm sorry, I must not have hit the second very well. We can go into that plot. And instead of having the Y list be for the surface area right now, we can actually choose from our lists the residual. And it might be down here pretty far. There we go. So there's our residual. And when we graph this, that scale is going to change a little bit. Again, I'm going to take off that function for a moment. But I just want to look at that residual. And again, the x-axis that we're used to looking at, that horizontal line, is essentially our model. And we can see these points above and below our model. So it did kind of okay here, but then we realized our model is just not doing really great here because of those outliers. So I wanted to show this pumpkin data. I apologize. I didn't get the chance to talk as much about end behavior. But one of the things I really like to talk about with students is when we have these models, like we did with this quadratic right here. what's happening theoretically with this? And in this model, does end behavior make sense in the context of pumpkins? So in other words, as I continue to increase my radius, does it make sense that the surface area is going to go up and up and up and up in a very quick way? And because technically for the function, we would say that as the radius increases infinity, then so would our surface area. But then they start to ask themselves, like, could this really happen? Could you really have a pumpkin grow infinitely? Are there any types of constraints? So there's this great conversation that we can have about end behavior in theory and end behavior according to the data. Matt, the good news is I can send you this data right after this webinar, and you can just take out those outliers and play around with it yourself. In fact, I hope you do. Looking at the clock with 8:55 on the clock, I do want to go ahead and give you one more thing. So the last thing I said was pretty cool to look at was looking at the weight. And the reason is, well, you know what? I'm not going to give anything away. I've got enough time. I don't need to be rushing. When I do this with students, I spend a couple days on it. And the reason is there's so many good examples for students to make sense of. I do want to show you guys what happens with weight. And so if we plot radius versus weight, I'm going to do zoom stat. I want you to put in the chat, that's looking very curvy. And when my students see curves, they normally have two answers. It's quadratic or it's exponential, because that's what they've been working on since they were in 9th grade taking, I apologize. Oops, there we go. So since they were in Algebra 1, they've been working on these models that were exponential and quadratic. And so every time they see a curve, they're like, oh my gosh, it's one of those two. But I want you to say in the chat, if we're comparing radius to weight, given the context, what do you think that one would be? While you're doing that, I'm going to get just a little bit ahead of myself because we've got a calculator drawing coming up after this. And I want to make sure that we don't go over time. We want to make sure we've got this. And give them enough wait time, Gail. You know what? That's not fair to her. But I'm going to still show. Let's check out this cubic with the radius versus the weight. And once you start thinking about the relationships, the mathematical relationships between these, I think it starts to make sense why this function would work. Let's go ahead and look at that graph. That, yes, a cubic works because we've got these 3 dimensions now coming in, and the weight is related to the volume, and that's why they study density in middle school. And so this is kind of a fun way for them to start to make all those connections. So again, talking about mathematical models first and then having them analyze the data, I think it makes for much richer conversations. And it helps students really try to like connect all the dots here. So we said that we would give you a little bit more about where you could find these resources. One of the best places, and Gail's done a lot of work on this, is education.ti.com. And there's actually a section in the resources called mathematical modeling, and you can find great big data sets and have fun looking over that. I also pull from the science section. Earth Science has a really cool one on lunar phases, which are very cyclical. If you're about ready to teach sinusoidal modeling, that one's a good one. And so we've added some of these links. Again, check out the PowerPoint when you get the resources after this one. And then Gail does a nice job of showing us more about logarithms. So at this point, Mike, you've got a whole minute. Are you ready to announce our winner?
I'm ready. Maybe I'm ready. All right, we are giving away to one lucky winner a TI graphing calculator of their choice, and tonight's lucky winner is Thomas Decker. So congratulations, Thomas. We'll be in touch soon to get some information from you, but start thinking about that. If you would like the documents for tonight, that is going in the chat window right now. And the certificate of attendance is also going to be in that chat window. We're going to be off next week, but back in 2 weeks with some Python coding and drones. It's supposed to be, I think, pretty interesting and exciting. So come back and join us in 2 weeks. And if you are having issues with these links, just hang tight. You're automatically going to get a follow-up email within a couple days, and it'll have all the good stuff, the certificate, the documents, and the recording as well. So huge thanks to Gail and Rachel for everything they put together for tonight. We really appreciate it.
Thanks, everybody, for being here.
Thanks again,
everybody. Have a
everyone.
good rest of your Tuesday.
Yep. And we hope to see you back real soon. Have a great night.